Hi friends, myself K. Lakshmi, Assistant Professor in the Department of SNH, Chebrolu Engineering College, Class 12, topic Resolving Power of a Grating. Now in this video, I would like to share about what is the Rayleigh's criterion for resolution, resolving power of grating, resolving power of telescope, and finally resolving power of microscope. What is the statement said by Rayleigh's for resolution? Two sources are resolved by an optical instrument when the central maxima of one diffraction pattern falls over the first minima of other diffraction pattern and vice versa. Here the examples for the optical instruments are prism, grating, telescope, microscope, and our eye is also the best example for optical instrument. So, the first concept about resolution is explained by the scientist by his Rayleigh's criterion for resolution. So, what is the meaning of his statement is, it is the central maxima of one diffraction is overlap with the first minima of another diffraction pattern. In the similar way, another central maxima is overlap with the first minima of this wave function. So, for this, he explained its criteria basing on three concepts: just resolved, not resolved, well resolved. Now, let us consider two wavelengths and by a grating, that means with the help of grating, resolve two wavelengths. When the difference between the wavelengths is very small, that means very nearly equal wavelengths. The nearly equal wavelengths can be explained as lambda, and the nearest wavelength is lambda plus d lambda, and such that the central maxima of the wavelength coincide with the first minima. The resultant intensity curve shown a thick curve. The curve shows a dip in the middle of the two central maxima. That means the two wavelengths can be distinguished from one another according to Rayleigh's criterion, said to be they are in just resolved case. If the difference in the wavelengths is such that the principal maxima are separately visible, then there is no distinct point of zero intensity in between the two wavelengths. Hence, the case is said by Rayleigh resolved. And the third case is not resolved. When the difference in the wavelengths is so small, the central maxima corresponding to two wavelengths come very close to each other, then the resultant curve shows without any dip. This curve is only one wavelength somewhat bigger and stronger. Hence, according to Rayleigh, the two wavelengths are not resolved. These cases we can observe by through this diagram. Here, when you observe that this is one of the wavelength, its wavelength is represented by the letter lambda 1. Another wavelength is represented in dotted lines. When you observe the difference between the dotted lines and dark lines, here the dark lines wavelength is represented by lambda 1. The dotted wavelength spectral lines are represented as a lambda 2. Whatever we discuss in the slides, here these wavelengths are very nearly equal wavelengths. So here when you observe that lambda 1 is the one of the spectral line of the object, let it be A. Lambda 2 is the one of the intensity distribution curve or Fraunhofer diffraction curve for an object B. When we observe through an optical instrument, when it shows the separate images of the two closed objects having nearly equal wavelengths, then we simply say that the optical instruments is well resolved. At what case we said to be well resolved means the central maxima and the first minima are not coincide. That means they are in a distinct position. If the optical instrument cannot show the image perfectly, that means whether it may be in the case of not resolved or just resolved. So what is the meaning of just resolved? As we said, the different wavelengths here. One is a dark line here. That wavelength is lambda 1. Another spectral lines having wavelength lambda 2, that is in a dotted lines. It is a clear picture when you observe that the central maxima of one of the spectral line is coincide with the central maxima of another spectral line. That means here the first minima is formed at the central maxima of lambda 2. The first minima of lambda 1 is formed at the central maxima case. Due to that, the outer spectral line gives a dip between the two spectral lines. That means by observing the dip, we imagine that here there are two objects are there. That means just a confirmation. So this case is a just resolve case. Whenever the central maximas of both are coincide, then the outlet of the spectral lines look like a single spectral line. That means no resolve. The cases of resolve, no resolve, just resolve, or depending upon the resolving power of optical instrument. For example, our eye cannot observe the stars on the sky. Why? Because our eye resolving power is small. But with the help of telescope, we can observe the stars, number of stars and their image perfectly, because the resolving power of telescope compared with our eye is more. What is meant by resolving power? A resolving power means the capacity or capability of an optical instrument which will show the separate images of very closed objects, that means very closed wavelengths, is known as resolving power. As compared with the telescope, microscope, our eye resolving power is small. That's why we cannot clearly observe the stars on the sky. But with the help of telescope, we can clearly observe the number of stars, their size, their shape, like that. And also, depending upon the size of the telescope, we can clearly observe the planets on the sky also. The depending upon the resolving power of the optical instruments. That's why here we discussing about the resolving power of grating. Why? Because grating is also an optical instrument. So, resolving power of grating. The definition of the resolving power of grating. It is defined as the capacity of a grating to form separate diffraction maxima of two wavelengths which are very close to each other. The resolving power of a grating is measured with a formula lambda by d lambda, where d lambda is the smallest difference in two wavelengths. As we know, lambda is the wavelength of the light, or it may be a wavelength of either of them, or mean wavelength it can be taken. Here we have to take the case just resolve case. So what is meant by just resolve case? It can be observed again in the picture. This picture gives the just resolve case. What is the meaning of just resolve case? The first minima of is coincide with the central maxima of another one, and vice versa. So, basing on this just resolve case, here we developed a formula for resolving power of grating, that is lambda by d lambda is equal to formula. So this is the picture. Here it is a monochromatic light. With the help of a convex lens, they can be converted into parallel beam of rays. Here the dotted lines indicates the grating. Grating is, as we already discussed, that it consisting of number of slits. Here XY is a screen. The dotted lines here indicates the lines which are travel in a same direction, that is as in initial direction. After the grating also they travel in a same direction. That means they have no angle of diffraction. Theta is equal to 0. And the next, when you observe that, here we have to take two spectral lines. The spectral line one is lambda. It is represented with a dark line. There is another spectral line, that means the nearest to lambda. That nearest is explained in terms of d lambda. The meaning of d lambda is very, very small. Lambda plus d lambda means it is a nearest to lambda. Now this wavelength is spectral line is represented by dotted lines. So here on the screen we have to observe a just resolve case. What is meant by just resolve case? The minimum of lambda plus d lambda formed at central maxima of lambda, and the first minima of lambda formed at central maxima of lambda plus d lambda. it is a clear, just a resolve case. Here the wavelength lambda makes a diffraction angle d theta n, and the wavelength lambda plus d lambda make an angle d theta n. When you observe the diagram, here P1 is the central maxima having wavelength lambda and the angle of diffraction is theta n. P2 is the position of central maxima having wavelength lambda plus d lambda with an diffraction angle theta n plus d theta n. That is very important point. So once again here I repeated, P1 is the position of central maxima having wavelength lambda with a diffraction angle theta n. P2 is the position of central maxima having wavelength lambda plus d lambda with an diffraction angle d theta n. Now AB represents the surface of plane transmission grating having grating element E plus D. As we know, E is the width of the slit. Each slit in grating, each slit having same width. So that width is represented by the letter small e, and D is the opaque space between each slit. That is also same for each slit. So E plus D is named as a grating element, and in this grating it have n number of slits. Now a beam of light having two wavelengths lambda and lambda plus d lambda is normally incident on the grating. P1 indicates the, as already we have to discuss in the diagram, P1 indicates the primary maxima or principal maxima having wavelength lambda and angle of diffraction theta. P2 represents the primary maxima of wavelength lambda plus d lambda at a diffraction angle theta plus d theta. So here it is theta, it is d theta. Now P2 position is here. So the total angle is theta plus d theta. According to Rayleigh's criterion, the two wavelengths will be resolved if the principal maxima of lambda plus d lambda of nth order in a direction theta plus d theta falls over the first minima of nth order in the same direction of theta plus d theta. Here the first minima of lambda in the direction of theta plus d theta. That means, as the condition from Rayleigh's criterion just resolve case, when you observe that the lambda wavelength central maximum is at point P1 and the minima is at point P2. So here the P2 wavelength is lambda, that means it is a spectral line, the lambda wavelength, but angle is theta plus d theta. That means for a wavelength of lambda, P2 is the position of first minima at an angle of theta plus d theta. Here it is the P2. P2 is the position of first minima of wavelength lambda with an angle of theta plus d theta. So the condition for principal maxima having wavelength lambda and theta direction by grating, as we already discussed in the Fraunhofer diffraction due to n slits, E plus D sin theta is equal to n lambda. Here, this is the condition we have to take from minimum. So, the minimum equation condition in Fraunhofer diffraction due to n slit is n into E plus D sin theta is equal to m lambda. Here, m takes all integers, that means n minus 1, 1 comma, 2 comma and 3 and so on, n minus 1, n minus 2, like that. But except 0, n, 2n, small n, capital N. Because these values of m gives the condition for order of principal maximas. Thus, the first minima exist in this case at an angle theta plus d theta. For this, we have to substitute the value of m as small n into capital N plus 1. That means the condition is the same, but the minimum case is obtained at a wavelength lambda is okay, but the angle is varied here. That angle is theta plus d theta. For this purpose, we have to change the m value as small n into capital N plus 1. Now in the same formula, just change the theta value as theta plus d theta and m value as small n into capital N plus 1. So this equation is like that. N into E plus D sin of theta plus d theta is equal to small n into capital N plus 1 lambda. So simply this is the final equation. What we have to get, that is minimum equation at point P naught having wavelength lambda with an angle of diffraction theta plus d theta. So simply by cross multiplying n, then we get equation E plus D sin of theta plus d theta is equal to n plus 1 by n lambda. Here n got cancelled. So this is the equation. As we know that principle of maxima equation with an angle of lambda and theta is simply E plus D sin theta is equal to n lambda. In the same formula, just we have to change the values in place of lambda, lambda plus d lambda, and in place of theta, theta plus d theta. So the principal maxima condition for these values is E plus D sin of theta plus d theta is equal to n into lambda plus d lambda. So these are the equations 2.47 and 2.48. Now by equating these equations, that means on LH side both equations are equal, then compare the RH side, then we get the finally small n 1 by n into lambda is equal to small n into lambda plus d lambda. Now multiply the lambda, n lambda, lambda by n is equal to n lambda plus n d lambda. On both sides n lambda and lambda will be cancelled. Therefore lambda by n is equal to small n into d lambda. Now cross multiply that. Finally we get the formula for resolving power of grating. As we already started in the starting slide, we discussed that the resolving power of grating is represented by lambda by d lambda. So finally we get the formula for lambda by d lambda is equal to small n capital N. Here n is order of the spectrum that will be discussed in the grating spectrum class. What is the spectrum with the help of grating and how many orders are possible with the help of grating. That will be entirely discussed in the class of grating. Here capital N is the total number of lines or slits on the grating. In this formula, the resolving power has no units. Why? Because here lambda units are angstroms and d lambda units are also angstroms. So the lambda by d lambda has no units. That means the resolving power of grating has no units. So this resolving power of grating is directly proportional to order of the spectrum and the total number of lines or slits on the grating, that is capital N. So this is the final formula for resolving power of grating. So once again I repeat that resolving power means the capacity or capability of an optical instrument which will show the separate images of very close objects having a nearly equal wavelength. So next we discuss about the another type of optical instruments like telescope and microscope. So the resolving power in the case of telescope, here we discuss in a simple manner. In the next class we briefly discuss about the resolving, how to find the formula for resolving power of telescope and also resolving power of microscope also. The resolving power of telescope is defined as it is the inverse distance or angular separation between two objects which can just resolve when we view through an optical instrument. So here generally telescope is used in the case to observe the stars, that means very long distance, very far distance objects like stars and planets in the galaxy, like that. So in telescope very close objects such as stars and stars of galaxies subtend very small angles on the telescope. To resolve them we need a very large apertures. We can use Raleigh's to determine the resolving power. So the angular separation between two objects must be delta theta is 1.22 lambda by d. Here, as the definition of resolving power of telescope, the reciprocal of angular separation. General, the angular separation is indicated by the formula del theta is equal to 1.22 lambda by d. So here the resolving power of telescope is reciprocal of angular separation. So that is 1 by delta theta is equal to formula d by 1.22 lambda. Here d is the diameter of the aperture and the lambda is the given light source wavelength. As the higher the diameter, the resolution is very good. That means the best astronomical optical telescopes have mirror diameters as large as 10 meters to achieve the best resolution. Also, longer wavelengths reduce the resolving power and consequently radio and micro telescopes need larger mirrors. That means to observe the planets and stars in the galaxy, they need or they, to for best resolution, they need large mirrors. So this is about the resolving power of telescope. And the next case is, and the next optical instrument is microscope. So the first microscope is used to observe the bacteria, virus. That means very small objects we cannot observe through our normal eye. So with the help of a microscope, we can observe the such a virus and bacteria like that. So what is the resolving power of microscope? So for microscope, the resolving power is the inverse of the distance between two objects that can just resolve, and the resolving power of microscope was explained by Ernest Ebb in 1873. Actually, the distance between the two objects is delta D is equal to formula lambda by 2n sin theta. As the definition of resolving power, inverse of the distance between the objects. So simply 1 by delta D is equal to 2n sin theta by lambda. Here the n represents the refractive index of the medium separating object and aperture. Note that here high resolution n sin theta must be large. This is known as numerical aperture. So this is about the concept of Rayleigh's criterion for resolution. That means the three cases: not resolved, just resolved, well resolved cases, and the different types of optical instruments, their resolving powers like grating, telescope and microscope. The previous explanation for a resolving power of telescope and microscope that will be discussed in the next class. Thank you.